Okay. Well, thank you.
So let's, before we move on to the class, let us also look at this another invariant form. So I hope you still remember that about this. This is also a jumping game. So let's say we have 9 pieces here. And then we are doing a solitaire game so that 谢谢谢谢。好，谢谢三门，三门可以帮忙把这个，谢谢。OK。哎，行，谢谢。OK。So I hope you still recall we have a game like this, and then we want to do what? We want to jump the piece over the other, as in the assignment question, but the target is to have exactly 1 piece left. Is that okay? So if we start with 2 by 2, then we can jump this here, and jump this there, so that we have only 1 piece left. In fact, we have shown that whenever the side, am I correct, is not a multiple of 3, then we can always do the cancelling, so that exactly 1 piece left. But then, the curious case is when each side is a multiple of 3. So let's say this is a 3 by 3 case. We want to show that it is impossible. No matter how clever you are, it is impossible to find a sequence of moves such that exactly 1 piece will be left in the end. Okay, and to prove this, a simple idea. Okay, it turns out that this is a difficult problem, but the proof is simple. Okay, a simple idea is to make use of the invariant concept. Okay, so let's assume that we have a grid. So to put these chess pieces, so we have an infinite size grid. Okay. Maybe. Okay, this grid is colored in a strange way because we look at 3. Okay, this grid is look at something like this. So we have a certain column with no colors, and then after a certain column, we skip 2 so that the next column here will have no colors. Is that okay? And similarly for rows. A certain row will not have any color, and after 2 rows, you don't have any color. So basically, so after doing this, what do we have? So this has no color, this has no color, so we will have color here, 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 and then colored here, colored here, colored here, colored here. So imagine this board is of infinite length. So we will have a color here, colored here, colored here, colored here. Is that okay? Is that okay? So of infinite size. Okay? Of infinite size. Now let's take a look of what we are going to put the pieces here. 3 by 3 originally on this board. If 3 by 3 is put here, 1, 2, 3, 4, 5, 6, 7, 8, 9, it will cover 4 black squares. Is that okay? If you move a little bit, shift by one right, then it is also covering 4 blacks. If we go up, this same 4. If we go up, 4. If we move like this, then we will have what? So go up and go 1 right, we will have something like this. So in any case, we will see that no matter how you place the pieces originally, it will always cover 4 black squares. Is that okay? Okay, we claim that. Okay, so at the beginning, initially, it will cover 4 black squares. we claim that there is an invariant of what is going to happen. The invariant that we are going to see is the number of black squares covered by the pieces is always even. So invariant. Always even number of black squares. Okay, to see this, we just need to analyze different cases. So what can we change of our configuration? So we have a white piece, we have a white piece, we have a white. So maybe let's say we have, let's say this is a black, let's say this is a black. Is that okay? If you jump one black over the other, what will happen? Jump one black over the other. So if this is occupying a black place, this is occupying a black square, then what will be the square here? By our coloring scheme. Black, black must be white, right? So if you have black, black, so you don't have this one anymore, you don't have this one anymore, and then this will occupy a white position. Is that okay? So the number of, in this kind of movement, if we are jumping a black piece over another black piece, then you get a white piece. So the number of blacks decreases by 2. So if it's even at the beginning, then it is even afterwards. Is that okay? So how about a black jumps over a white? What will happen? What will happen? If I have a black, I jump over a white, I will have a black. Is that okay? So these two are gone, but then I will have a black. So the number of blacks does not change. So if it is at the beginning even number of blacks, then after this movement, it will still be even number of blacks. Does that make sense? Okay, and then, so there are other 2 more cases. If it is a white jump over a black, what will happen? What will happen? So everything is symmetric, right? If you have a white and the black, white, black, the next one has to be black. Is that okay? So these 2 are gone, but then I will have a black. So the number of blacks remain to be the same. Even, then even. And there is one last case. If it is a white, it jumps over a white, then what will happen? So if it's white, white, it means they are in the same column or in the same row, white. So you got a white. So the black doesn't change. Even, even. Okay? So this is the behavior if we try to color the board like this. Okay? Now, we want to show that it is impossible to have exactly one piece remaining. Why? Okay. We want to show this by contradiction. Okay. If there is a super smart person in the universe that can find moves such that exactly one piece is left in the end. Let's say there is a certain person. So after, so this person, let's say there is a certain person. Let's say this is a crazy scientist. So move this, move that, and then move that, and then move that, whatever. Okay, so after using some movement M, you could have exactly one left. Exactly one left. Then using our observation, where will that piece be? Will that be in a white square or will it be in a black square? It will be in a white, right? White. Because you can always have even number of blacks. So if you have just one piece left, it must be in a certain white position. Is that okay? A certain white position. Let's say this is in a certain white position. Okay, a certain white position. Okay, now, let's say, so for any white position, you can find a surrounding position with something like black. Let's say this is the position that is in black. Is that okay? Is that okay? Now, what we are going to do, we are going to secretly shift the beginning configuration of this one into this direction one step. So at the beginning, the crazy scientist is moving this one in a very large board. But what we are going to do, we are going to shift everything one step over this direction. So it will occupy this location instead. Okay, let's say. And then we will ask the scientists to do the same moves again. Exactly the same moves again. What will happen? Where will be the piece in the end? Originally, the piece is here. But then we are moving the 9 pieces, one in this direction at the beginning. You do the same move. Then the last piece will now be in this location. Does that make sense? You are applying the same move, right? The same moves. If it ends at this one before, it must end at this one this time, because everything is shifted one position over there. Is that okay? But then this will create a contradiction, because in that case, we will have one black pieces left at the end. So what does that mean? It means that if there is a way to move the pieces so that exactly one is left, there will be a way to move the pieces so that in the end, it will be landing on a black square, which is impossible. So because of this, because it is going to be impossible, then what does that mean? The original assumption is wrong. There is no way to move the pieces so that exactly one will be left in the end. Is that okay? So this proof works. Whenever you are talking about 3 by 3, you can also talk about 9 by 9, whatever, 6 by 6. You put it on the same board, you will see same effect. Is that okay? Is that okay? Because if we have 3 by 3, it is even. 6 by 6, or actually 3 by 6, there will be even black squares covered by here, even black squares covered by here. So in the end, it is even. And then, so we can go to the same proof. If there is a way that you can have exactly one left, it has to be a white. But then you cannot guarantee to be a white all the time. So in that case, if you start by 3 by 3, 3 by 6, 6 by 6, or whatever, then you cannot. There is no way that you can move the piece so that one is left in the end. Is that okay? Okay. So yeah, I hope you like this. Okay, so we don't have much time, but I think it is sufficient to talk about this fundamental theorem of arithmetic. So we are going to talk about this fundamental theorem of arithmetic. So this is actually like each integer has a unique prime factorization. So unique prime factorization. So how can we prove? Okay, so one thing is that this is what we have talked about last time. Okay. So we have defined what is prime, right? And then we have this lemma that we can have. So suppose that P is a prime, and then we know that P divides A and B, multiplied together. Then it implies what? It implies that P divides A or P divides B. Does that make sense? Okay, the reason is that, okay, we can first ask if A and P has common factor. If A and P has common factor, then P divides A, because P is a prime. Now, if P and A does not have common factor, then we have shown something like if this one and this one, the GCD is equal to 1, then this one has to divide this one. This is from a certain lemma we have done last time. Is that okay? So either P automatically divides A at the beginning, or in case P does not divide A, the common factor between P and A is exactly 1, so that we can have P divides B. Is that okay? Okay. Now similarly, we can extend this. Suppose that P divides A1, A2, A3, ... up to AK, the product of these things. Then this will imply what? P will divide AI for some I. Is that okay? So this is actually an extension of this one. You can prove it by induction. Either P divides A1. If not, then P must divide the product of the remaining part. So by induction, P divides one of them. Is that okay? Okay. Now, so what is fundamental theorem of arithmetic? So it says that every integer there exists a prime factorization of it, and such a prime factorization is unique. So you can, if you want to express it, so you can write down n to f for every integer n greater than 1. N can be expressed as a product of prime P1, P2, ... up to P, let's say Pk, such that P1 is less than or equal to P2, less than or equal to P3, up to less than or equal to Pk. These are primes in a unique way. Okay, so this is the fundamental theorem of arithmetic. For every integer n greater than 1, n can be expressed as a product of primes. And then this expression, if you sort the primes from small to large, this is unique. Okay? Okay. And then, yeah, the proof is going to be super simple. So here, this is what I've mentioned last time. If you want to show something that is unique, what you are going to do is you first show that it exists. And then you want to show that it is going to be unique. Is that okay? So this is to show that it is unique. So first of all, it must exist. And now, if it exists, then there is no two other ways. So it will be going to be unique. Okay, so the proof is like this. So the proof will be so we want to show that this is for every n there exists a prime factorization. There exists a prime factorization. So that's easy. We prove it by induction. So basis case is, so we have the basis case, n is equal to 2, and n is equal to 2, done. So this is done. So it's trivial. It's done. Okay? So inductive case, we are going to use strong induction. So we assume that for n is equal to 2, 3, up to k, there exists prime factorization. Now, when we talk about n is equal to k plus 1, there are going to be two subcases. We have two subcases. So the first one is k plus 1 is a prime. The other case is k plus 1 is not a prime. Is that okay? Is that okay? Now, if k plus 1 is a prime, then it itself is a prime factorization. So this part is done. Is that okay? Now, if k plus 1 is not a prime, then what does it mean? Then it implies take out a prime factor. Not need to be a prime factor. Take out a factor. So you can write down. Or alternatively, in that case, your n is equal to k plus 1 can be expressed as a product of two numbers, right? Two numbers, whatever. How do we call? Xy, okay. N is equal to xy, such that xy, they are both less than n, and they are both greater than 1. Is that okay? Is that okay? Now, induction hypothesis says that x will have a prime factorization. Is that okay? And then y will have a prime factorization. Is that okay? So in that case, if this is the case, then n will have a prime factorization. Is that okay? If you're okay with this, could you please raise your hand? Okay, so the whole thing here is, the whole proof here, we show that existence work. So it is, there exists, existence, okay. So what it remains is, we want to show that the prime factorization is unique. And then to show that it is unique, we prove it by contradiction. Okay. To show uniqueness, we show by contradiction. So what do we do? So suppose not unique. So we suppose to the opposite, to the contrary, sum of the number n has two or more factorization, different factorization. Then so if there are if there is some number with two or more factorization, let's find out one which is the smallest. Let us get the smallest such n. So n can be written as some prime factorization p1, p2, p3 up to pk. And then n can also be written as some q1, q2, q3, up to qm, let's say. Is that okay? So there are two different factorization. But then all of these numbers are primes. So these are primes. So these are primes. Is that okay? And these are primes. Is that okay? Okay, now, 2 says, if there is a prime that divides a product of primes, then, or a product of numbers, then P divides exactly one of them. Or more, not exactly, at least one of them. So here, let's take a look. So we know that P1 divides n, right? Right? And then n is equal to what? N is equal to q1, q2, up to qm. So P1 divides qi for some I. Does that make sense? But qi is a prime. So we must have qi is exactly equal to P1. Is that okay? Is that okay? P1 divides qi, and there's no way that qi can be made smaller. Or the largest common factor between P1 and qi is now P1. So qi has to be, if it is a prime, it has to be exactly equal to P1. Is that okay? So this implies we can get some n prime, and n prime is equal to P1, P2, no, not P1 anymore. So you try to divide. So n prime is equal to a number such that you divide n by P1. Or, because P1 and Qi are the same, so we have, it is the same as if n divided by Qi. Is it okay? So we have this one is equal to what? This is equal to P2, P3, dot, 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 up to Pk. And then this is also equal to Q1, Q2, dot, 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 up to Qi minus 1, Qi plus 1, dot, 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 up to Qn. Is that okay? Is that okay? Now, if these two are different, we cancel the same parts, P1 and Qi, then these two will remain to be different. Does that make sense? Well, we get a contradiction. We assume n is the smallest number with two different factorizations. But we now get a smaller number, n prime, with two different factorizations. So we get a contradiction. Okay? So contradiction now. So what does that mean? So when we get a contradiction, so this is wrong, it means that for every integer n, it has exactly one prime factorization. Okay, that's it. Yeah, that's all. So next week will be the exam, and after that, we will continue the discussion on number theory. We will start a new concept called modular arithmetic. So let's talk about that after the exam. Thanks.